Good morning, good afternoon, and good evening, and welcome to the 10th International Conference on Scour and Erosion, or ICSE 10, and the first virtual conference of the ICSE series. The ICSE is a biannual and a truly international conference joined by the geotechnical and hydraulic engineering communities to share new findings on the understanding, evaluating, and remediating scour and erosion. While celebrating such achievements, we have even more reasons to be thankful for the resilience of the international community in these challenging times. Also, the successful after the ICSE 5 in San Francisco in 2010, we anticipated the return of the ICSE to the US and in the beautiful fall of the Washington, D.C. area last year. However, we know the pandemic has interrupted every aspect of our lives, including the ICSE. Yet we are so grateful of the support from all of you, so that we are, with great excitement and anticipation, finally beginning the conference today. We really want to thank all of you for making it happen, and we also appreciate very much the support from the American Society of Civil Engineers, Geo-Institute, and their staff for working tirelessly behind the scene for making the conference a reality and also a success. Well, in the next 3 days, and you will interact with over 160 participants from many countries and regions in many time zones. And you can also attend six keynote lectures and 105 technical presentations in 20 technical sessions. There are also 4 very educational and informative short courses on the 4th day, this Thursday. And don't forget to attend the 2 very exciting virtual tours on this Wednesday afternoon, where you can witness the state-of-the-art hydraulic lab and some research projects of the Federal Highway Administration, and also the one-of-a-kind and large wave research laboratory at Oregon State University. Well, another high note of the conference is the open access proceedings of over 1,500 pages, and they include 137 full papers and 5 abstracts of keynote lectures. And each paper was peer-reviewed by 2 reviewers. The publications cover 14 broad topics in scour and erosion, and you will hear the live presentations of most of them in the next 3 days. They represent the state of the art and the state of the practice of scour and erosion, and the most recent achievement by researchers, practitioners, policymakers, and the general public. So again, want to thank all of you for joining us today and in the next 4 days. And I hope you also get to connect and mingle with colleagues on the virtual conference platform, with your coffee or tea, whether it's your midnight or mid of the day. Well, I'd like to first start with our first keynote speaker. And well, altogether we have 6 keynote speakers, and 2 this morning in the US Eastern Time, and 2 tomorrow on Tuesday, and also 2 on Wednesday morning. Our first keynote speaker is Mr. Hari Kalla, and and the keynote usually is about 15 minutes, and we usually first give a brief introduction of the keynote lecture, and then the keynote lecture would last about 40 minutes, and in the end, we'll have the Q&A sessions. Well, in 2019, Mr. Hari Kalla was selected for Senior Executive Service position of Associate Administrator for Infrastructure for the Federal Highway Administration, or FHWA. As the Associate Administrator for Infrastructure, Mr. Kalla serves as a member of the FHWA's leadership team and participates in developing strategic initiatives that have a broad national impact upon the agency and the nation's transportation systems. Prior to this position, Mr. Kalla served as the Associate Administrator for Research, Development, and Technology, where he provided executive oversight to FHWA's National Highway Research and Technology Programs. And prior to his most recent appointment, Mr. Kalla served as a director in the Office of Pre-Construction, Construction, and Payment within the Office of Infrastructure. In this role, Mr. Kalla provided national leadership in the pavement technology and construction engineering to FHWA's headquarters and field offices, state and local government, industry, and academia. So with our great honor and pleasure, and we welcome our first keynote speaker, Mr. Kalla.
Ming, thank you. Good morning, everybody. Let me start sharing my screen. So please tell me when you see my presentation, and then we'll start. Ming, can you confirm if you can see my presentation?
Yes, we can see it.
Okay, thank you. So good morning from Washington, D.C. That's where I am. I'm so honored and privileged to be part of this conference. The Federal Highway Administration, we have a number of folks from Federal Highway Administration at this conference. And I think that having these type of conferences and participating at these conferences is so important. We learn so much through the exchanging the ideas and sharing new information. And I think we all better off by being part of such events. So thank you for inviting me. Before I talk about the Federal Highway Scour program, let me just quickly touch upon what's happening in the Washington, D.C. with respect to the funding of our highway program. As you may have heard, that the Senate passed the Infrastructure Investment and Jobs Act in August, actually on August 10th. And on the House side, the current goal is to pass this bill by end of this October. We are operating under the extension right now because our previous authorization FAST Act expired end of September. Now, I have to tell you that this is a very historic opportunity and historic moment in infrastructure investment. And this bill provides historic policy prescriptions as well as investment for the infrastructure. This bill, IIJA, includes about $550 billion in the new federal infrastructure investment, along with the 5-year reauthorization of surface transportation programs. These new investments include roads, bridges, mass transit, water infrastructure, resiliency, and broadband. The part which we are really interested in is about $350 billion over 5 years of highway funding. $300 billion is a part of the Highway Trust Fund, which is about 29% increase over the current funding level. And in addition to that, there's a $47 billion of transfer from the general funds to the highway funding. So it's a significant bill. It establishes approximately a dozen new programs supporting the priorities such as resiliency, carbon reduction, bridges and culverts, electric vehicles, and connecting communities. Some of the policy highlights of the bill includes reducing the greenhouse gas emissions. There is a new formula program, and there are a number of policy ideas for a new EV vehicle charging infrastructure. For resiliency side, there is a new formula program, there are various grant programs, and there are other programmatic consideration for resiliency. And they're continuing with the MAP 21 and FAST Act, there are provisions to accelerate their project delivery. So again, I mean, this is a fundamental shift, a historic opportunity for us in infrastructure business. So stay tuned, there's more to come. Now, to Scour. Now let's talk about Scour a little bit, but let me start with the history of the Scour program. Believe it or not, the consideration of Scour, along with associated attempts to apply science and engineering into the bridge design, has existed for about 150 years. Obviously, the knowledge and understanding of Scour is now significantly more than that time. One of the important figure in the Scour investigation, Dr. Emmett Richardson, he wrote an excellent paper on the history of Scour research and programmatic effort. Dr. Richardson noted that bridge Scour research prior to 1949 was not systematic, and much of that was a single purpose research or reports of the Scour problem experienced at a particular bridge. And 1949 is representing the beginning of the effort of Dr. Emmett Larson from Iowa Institute of Hydraulics Research. He began such systematic research within the United States. And that's also about the same time when the US Bureau of Public Roads, the precursor of federal highways, start funding and supporting Scour research. Furthermore, in 1962, the failure of I-29 bridge over Sioux River in South Dakota taught us two things. One is that Scour could adversely affect even new major structures. And second, the discharge alone is not a predictor of how Scour forms at these highway structures. Next, we move to 1973. The Federal Highway published a report in 1973 to define the bridge failure and later provide data on the bridge failure from hydraulics related component. Clearly, Federal Highway and transportation community recognize the need for Scour research. However, there was various factors played a major role in not consistently applying research inside to the bridges. And that, when I say the various factors, the key factor, obviously, simply putting, is that Federal Highway lacked authority to consider Scour at the bridges in anything more than a research context. So furthermore, in 1968, we started to get our sort of kind of statutory framework with the passage of Federal Aid Highway Act that was signed by President Johnson. That led to 1971, when we promulgated regulatory requirement within our 23 Code of Federal Regulation to add national bridge inspection standards. However, NBIS at that time did not include or consider Scour. And actually on April 5th, 1987, Scour-induced collapse of the New York I-90 bridge resulted in 10 fatalities and disrupted a major interstate route. That incident was a major impetus for establishing the Federal Highways Scour program. During the NTSB's investigation, they summarized in their report that contributing to the accident was inadequate oversight by Federal Highway Administration. Subsequently, Scour-related bridge failure reinforced the need for Federal Highways oversight of Scour. Based on that particular bridge failure, Federal Highway initiated a response directing that each state should evaluate the risk of its bridge being subject to similar damage during flood in order of 100 to 500 year deterrent period or more. Federal Highways Scour programs current authorities are found in National Bridge Inspection Standard, NBIS, which is 23 US Code 144. The our current Scour program involves about 512,000 bridges, which is about 80,000 of all bridges in the United States. Within the NBIS, one of the Federal Highway's role is ensuring the owners have conducted Scour evaluation to determine whether their in-service bridges are vulnerable to Scour. For those bridges determined to be Scour critical, we ensure the owners have developed and are implementing the plan of actions and their associated Scour countermeasures to mitigate the risk of Scour. These countermeasures often call for installation of things like riprap or to protect the foundation, and in some cases, it may include the strengthening the foundation through the addition of piles, sheeting, or other appropriate measures. Also, the element of Scour program are guided by the design standard under our 23 CFR 650. So the Scour program is deeply rooted in our overall bridge program, and we continue to realize that it's a very complex phenomenon as it relates to the interaction of flooding water and wearing foundation components, as well as the consideration of hydraulic, structural, and geotech design programs. Historically, some of you may aware that the Federal Highway Scour program was established in 1988 through a publication of Federal Highway Administration's Technical Advisory, Scour at Bridges. This TA, this advisory included interim guidelines for evaluating Scour at the bridges. The TA provides Scour mitigation. The TA provides Scour mitigation recommendations for both new and existing bridges. The TA also described Federal Highway's intent to develop and publish a new Federal Highway publications, the Hydraulic Engineering Circular number 18, HEC 18. Also in 2004, Scour program has a legal authority under NBIS, currently under 23 CFR 650. So that was the time, and now you see that we have, since then, we have established quite a bit of statutory or regulatory framework to support the Scour program. So let me take a few minutes to talk about where we're going. Recognizing opportunities to improve the Federal Highway Scour program, the agency has adopted a common vision and implementation of forward-thinking next generation Scour program called Next Scour. The Next Scour program is an initiative with the goal to improve the design and analysis of a scour that affects bridges, culverts, embankments, and the primary goal of this initiative, obviously, is a bridge scour. Within the Next Scour initiative, the Federal Highway seeks to strike a balance of continuing the support of our current Scour publications, while also recognizing the need to advance the state of practice for Scour analysis through research to determine the worst case Scour depth. The abutment, the picture you're seeing, the abutment on the right was protected by riprap, but was removed by a flood event. I think this picture is taken in Illinois. I'm not quite sure the name of the bridge. The next, so who is our target audience? The design, actually the design engineers of all disciplines, whether they are generalists, they are hydraulics, geotech, structures, or operations. So obviously all the design engineers, construction workers, the operation and maintenance staff, all have an interest in safe bridge program. While the program is applicable to the larger group of engineers, the focus of the program will be providing the support specifically to hydraulics, geotech, and a structural engineer in charge of Scour analysis. Here are the some of the key things which I want to take with you. Much of today's discussion relates to the vision and current research initiative within the Federal Highway Next Scour program. Most topics are not currently included in our publications. However, this is a research initiative. It is a research initiative like this that have built our program, and we believe the research program, these research projects are very promising. Next, Scour seeks to develop a deeper understanding between two key factors that drive the scour prediction, hydraulic loads and geotech resistance. Next Scour will seek to generate a multidisciplinary framework to address scour prediction by improving partnership between hydraulic engineers, geotech engineers, and structural engineers where appropriate. Next Scour will continue to support the use of existing well-established scour equations by educating engineers on appropriate application and limitations in predicting the formation of scour. Federal Highway's goal is to regularly update our scour-related manuals and materials, including the HAC manuals, hydraulic design series, tech briefs, and NHI courses, and using the actionable and appropriate research and current practices. Next, will seek the input of hydraulics, geotech, and structural community, both from the practitioners, as well as the academic community, federal agencies, and the others for the development of program improvements. We intend to ensure transparency of development, but also ensure the final products meet the programmatic requirements, as well as providing functional products. Federal Highway expects the appropriate application of next Scour program concepts and tools will result in cost-effective and safe bridge design or water through an improved usage of existing tools and the development of improved accuracy tools that will continue to ensure the safe bridges on our highways. Federal Highway has proposed to update the NBIS to be consistent with the MAP 21 requirements and to update the Scour-related terms and activity updates. Now, you all know that I don't have to tell you that the water and hydraulics is among the most common reason for the damage and failure of highway bridges in the United States. Within these water-related occurrences, scour continues to be a significant contributor to the bridge failure. Federal Highway has provided owners with the series of scour-related publications to assist in the design of bridges that, if properly designed and constructed, would not be vulnerable to scour. Using actionable and applicable results of scour-related research and common practices, the Federal Highway aims to routinely update these manuals to provide owners with recommendations to address stream instability and potential scour. In coordination with the NHI, National Highway Institute, we are currently updating HAC 18, 20, and 23 and their associated training courses based on the advancement we have learned since their last update. Virtual delivery platforms are now available for many NHI hydraulic courses. Next Scour goal is to improve the scour analysis to meet the Federal Highway's strategic plan goals for safe, economical, and innovative bridge foundation design. Next Scour will accomplish this through adopting programmatic direction, research, and deployment of new innovative scour analysis approaches that account for hydraulics and geotech components. As stated before, Next Scour plans to improve the two major components of scour that includes water and hydraulics forces that cause erosion resistance of soil and associated geotech effect. Next Scour will accomplish this through a development of two focus areas, Next Scour hydraulics and Next Scour geotechnical. While geotechnical consideration currently exists in Federal Highway's HAC 18 manual, we believe improvements can be made to this methodology. As I mentioned before, there is a broad scour analysis assumption of a uniform layer of soil consistent of granular material that is characterized by the D50. I won't read both of these bullets, but you can see there are many facets being considered in the hydraulic loading aspect as well as soil resistance side of the equation. I want to discuss some potential improvement of scour analysis. The Feral Hive Scour next Scour vision is to continually improve the Scour program for each facet of the program, from hydrology to hydraulics to scour protection. As an example, the current state of practice for hydrology is where hydraulics engineers use the peak flow or the rate of flow versus time in designing hydraulic structure. Typical hydraulic practice estimates the peak discharge or hydrograph from historic stream gauge flow data, or for ungauged stream deterministic or methods. There are other methods available. However, the next scour recognizes the worst case scour in cohesive soils may not fully develop during a one peak flow event, but rather is a result of multiple flow events. To illustrate, perhaps we should be looking at how to represent a series of flow events over some service life that creates the maximum theoretical scour prediction. How could we do so where no gauging station information is readily exists? Are there means to describe some flow duration threshold so that in turn hydraulic models can be more readily consider the forces and effects of such situation on the stream, bridges, or embankment? Perhaps we need to enhance our understanding of hydrologic properties that might influence scour and the channel forces from geomorphic regional, watershed scale, and temporal spatial perspective as it relates to the transportation projects. The Federal Highway is working with USGS to look for the opportunity to enhance the hydrologic components for these new hydraulic methodology, including climate change. Federal Highway is seeing an increased interest by owners to improve their hydraulic modeling by using 2D model instead of 1D model. This is an advancement in modeling due to a better representation of hydraulic site condition. Many bridge owners and their engineers are applying improved survey data found in LiDAR data, which further improves the scour analysis parameters that are provided by these more advanced models. In addition to potential improvement to the hydrologic and hydraulic analysis parameters, Federal Highway continues to advance the state of practice for scour depth analysis by researching the geotechnical contributions the soil provides by resisting scour effect of water loads. Within the Federal Highway Research Program, there are currently 3 promising research initiatives. First, scour decay function. Second, 3D scour modeling. And third, reliability-based scour design concept. Let me very briefly touch on all those 3 initiatives. For the first initiative, the scour decay function. The current 5th edition of HAG 18 provides a discussion on rock scour for bridge piers using the stream power decay method. Federal Highway is developing a similar concept for scour in cohesive soils. The new idea will include water load decay functions for contraction, abutment, and pier scour. These concepts include the necessity to determine the site-specific soil erosion data. When combined with the water load decay function, the scour prediction may result in increased accuracy of scour calculation for foundation design. Federal Highway recently completed a proof of concept study with 19 state DOTs where we tested devices that generated water load versus soil erosion rates. 2 Federal Highway devices shown on the slide on the right. They are ex situ and in situ scour detection device. Federal Highway's Geotech lab is testing several other soil erosion testing devices. Our geotech lab and resource center staff are testing several soil testing devices to associate the soil erosion rate to soil characteristics. We are considering this an attempt to associate erosion rates to commonly obtained geotech data at most projects and possibly avoid the need to perform costly erosion rate testing of each project. Second research initiative about the 3D scour modeling. We see potential improvement in determining each of the component of total scour using 3D scour models. Whether the development is performed through the Federal Highway Research Lab or its contractor or through other entity, there are many hurdles to overcome with this approach, and it will take much coordination by the member of hydraulic and geotech communities. Some general steps for this research initiative include build bridge hydraulic related software and applications capable of modeling sediment transport, model simple and complex bridge components, build GUI to enter data for these conditions. Fourth step is develop the geotech stratigraphy and their erosion rates within the software environment. And the fifth and final step is perform many additional soil erosion tests to build a database of varying soil parameters. Now for the third research initiative, the reliability-based scour design concept. This is the purpose is to identify and evaluate the uncertainty associated with the bridge scour prediction, including hydraulics, and the model equation uncertainties. Reliability-based scour design concept are being researched. Our reliability-based design concept provides a powerful tool in quantifying the safety level of bridge and producing a strong support for decision-making in bridge construction and maintenance. Another research initiative underway is to determine the riprap countermeasures reliability. Shear failure and edge failures are two modes of failure for existing installation federal highways evaluating. So there's supposed to be a video on the screen, but unfortunately the video is not working, but that depicts our research on the edge failure. Next Scour program seeks to fill these gaps in the current Scour program by performing collaborative research to integrate geotech and hydraulic engineering and provide improved and engaging training that will help engineers effectively use the existing and future Scour tools. Now, what you see on your screen are some of the pictures of some of our state-of-art Turner Fairbank Highway Research Center hydraulic research lab, where much of the research I talked about today is being conducted. Please be sure to take a virtual tour of our hydraulics lab at the end of this conference. Next, I just want to touch very quickly on a few Scour design initiatives that provides for resiliency in bridges. Resiliency is a topic that Federal Highway is fully engaged in as we collaborate with the state and local partners to address the demand of climate change. Designing resilience into our infrastructure directly relates to our next Scour research. I mentioned the research being conducted by USGS to take probabilistic approach to predict the future hydrologic conditions into the Scour design process as we anticipate and prepare for worst case Scour conditions during the service life of a bridge so that it can withstand the worst case scenario. The use of 2D modeling will give more representative flow conditions that produce the worst case scenario. And we believe that the 3D Scour modeling has the potential to predict the worst case scour that needs to be considered in the final bridge foundation design that will yield resiliency into our bridge design. I'm not going to talk about this more about this slide because Mr. Joe Crolack will be presenting this information on Tuesday. So I strongly encourage you to attend his presentation to learn a little bit more about this particular topic. Federal Highway recognize that is in our best interest to utilize the expertise within the DOT practitioner, ASTRO, other federal agencies, consultants, academia to assist in our proof of concept as well as development of the tools that may be used in navigating the design process. As I told earlier, the 19 state DOTs are currently participating in a proof testing of Institute soil testing device to determine the soil erosion rates for various soil types across the country. There are other practitioners who are also performing soil erosion rates, and their subject matter expertise will be valuable in enhancing this methodology. For example, we recognize that Dr. John Louis Briaud will be presenting after me, continuing to research soil erosion rates. Federal Highway also has plans to continue testing other devices in our Turner Fairbanks lab to estimate soil erosion rates. Of course, you all are our stakeholders as well, and we definitely appreciate your efforts and your insight. So what's next? Like I talked about the NBIS rule update. So the NBIS provides the authorities and requirement that constitutes our Scour program. Federal Highway has proposed to update the NBIS to be consistent with the MAP 21 requirement and to include the Scour-related terms and activities updates. Once we issue the final rule, these updates to the NBIS will require delivery of a series of briefings on the Scour-related regulatory and programmatic updates and specifications for the National Bridge Inventory. Our next Scour long-term plan is to ensure that all bridge owners across the country have the tools and understanding needed to ensure their bridges are not vulnerable to a scour. Future steps involve improving our understanding of the scour phenomenon and providing support, which have been detailed throughout this discussion today. However, as computing power continues to increase and computing resources improve, obviously there are going to be more improvement in methods for calculating scour. Federal Highway has all parts of Federal Highway work very closely to provide the services to our stakeholders, and I want to acknowledge all those different teams. This effort is a partnership across our National Hydraulics and Geotech team led by Joe Crolack. The outreach and program support will be provided by, and the trainings will be provided by Resource Center and the Turner Fairbanks Highway Research Center. We also acknowledge the assistance and appreciation of all our colleagues in our federal lands program, as well as all 52 federal aid division offices. If you have any questions about any of the information I presented to you today, I'm just giving you the names of the folks, our technical experts, Paul Sharp, Cornell Kennedy, and Jennifer Nix. They are all at the conference. So please feel free to reach out to them if you have any questions. Now with that, I will turn it back to you, Ming.
Thank you, Mr. Kalla, for providing the FWA perspective of Scour. We have some time for questions. from the participants.
Right. Oh,
And this is the presentation is also broadcast live on YouTube. Wonder if you have any questions for Mr. Kalla. And if you do, appreciate if you can state your name and the country you're from, and then either feel free to type the question on the chat on the conference platform, or if you wish, you can also ask directly. Then you can please just turn on your camera, and they can ask. Either way is fine.
are you on Zoom? Yeah, I believe I'm on Zoom now.
Any questions? Sometimes there's a slight delay, and I'll give it just a minute and to wait for any questions to be typed, either on the chat, or if you wish, you can ask directly. So there's a question on the chat from Amir, and the question is: apart from scour on a bridge, scour around monopiles and jacket structure will be discussed in this conference. That's probably not a question for Mr. Kalla.
I'm not sure.
Yeah. But as you can see, from the conference program, and there are various topics, and we have 14 topics, and they are in the 20 technical sessions, and over 100 presentations, and so you could maybe find the topic related to what you're interested.
Ming, not seeing any question. I just wanted to again say thank you.
Ms. Kalla, there's a question, and I can see there's a little bit delay, and so the question is from Janet Bay, and the question is: would next Scour incorporate its own 2D modeling software, or use a different platform like SMS?
Frankly, I'm not sure. So you have all our federal highways experts. So Joe Crolack will be speaking tomorrow. And then we have Mr. Paul Sharp, Jennifer Nix, and Cornell. Please feel free to ask them. My apologies. I'm not quite sure.
Thank you. Do we have other questions? We understand Ms. Kalla is very busy, and thank you so much for taking your valuable time out of your busy schedule. So here's another question from Ulrich, and the question: thank you for a nice presentation, and nice to see that hydrodynamic load predictions are going to be more advanced. Are the related scour prediction formula that are now used advanced enough to deal with this increased detail in flow output?
So
your question.
Ming, thank you. Again, I mean, I have to sort of it's embarrassing, but I'll have to tell you that I'm not the scour expert. And I would strongly, if you have any technical question on the Scour program, I would strongly encourage you to, when you see Joe Crolack or Paul Sharp or Jennifer or Cornell, please feel free to ask them question. I apologize. I should be, but I'm not as well versed in this technical, the aspects, detailed technical aspects of the program.
Okay, thank you. So there's actually an answer from Paul and at FWA and on the chat.
All right, thank you, Paul. Appreciate it.
Last round, if any questions for regarding policies of FWA and if any question. Peter Toh asked, is there any possibility for international research to participate in your program?
There are mechanisms by which we participate with the international researchers. So I would, again, we always looking for input and insight from all sources, including the international researchers as well. So I would strongly encourage you to reach out to our federal highway researchers and our federal highway program experts and have a conversation with them. And I'm sure that we absolutely would love to work with you, but there are mechanisms to work with international researchers. So please reach out to us and our experts, and we'll look forward to those conversations.
Thank you. And there's another question forwarded by Brad Keeler and our Geo-Institute director. And the question he forwarded is, would like to know if FHWA has any documentation or guidance to design according to climate change effect.
I'm sorry, the question is, do we have any documentation of the climate change effects?
Yes.
Okay. So there's a lot of research has been done and being done on the climate impacts of the climate change. As far as the specific research products or the documents, I'll encourage Paul Sharp and Joe Crolack to type the answers if they have at the top of their head any specific documentation. But I know our work with the USGS and the White House, the work with the White House. White House has taken a lot of interest in resiliency and the impacts of the climate change. So there's a lot of work is being done. I don't have any specific the documents in my mind right now, but I'll ask Paul Sharp and Joe Crolack and those guys to provide any documents if they can think of.
Thank you. There's a question from Rodney in the UK, and Rodney asked, will Scour research benefit for the recently much increased spending on infrastructure?
Yes, of course, absolutely. Tell you this is an exciting time to be in this field. As you see the federal highway, there are a number of opportunities that are going to be to incorporate our new thinking on the Scour and our new thinking on resiliency in our bridge program investments. There are significant increase in investment for the bridge replacement for bridge programs. And then there's an entirely new program for the resiliency. So I think that those programs offer us a great opportunity to incorporate our current latest state of practice thinking into how we design and build those bridges. So absolutely.
Thank you. Any other questions? Thank you, Mr. Kalla and the FAW Associate Administrator for Infrastructure and for your valuable time and your perspective. We appreciate that.
Thank you for inviting me. I think it's a great time to be in this field, and I'm really excited, and I'm looking forward to this interesting dialogue that's going to take place. So thank you.
Thank you very much. So next, I'd like to turn to Dr. Jennifer Nix, who would moderate our next keynote lecture. So Dr. Nix.
Great, thank you, Ming, and thank you, Mr. Kalla, for your excellent keynote address. So moving on, I have the honor of introducing our next keynote speaker, who's one of the most prolific figures in the world of scour and erosion. Dr. Jean-Louis Briaud is a distinguished professor at Texas A&M University, a distinguished member of the American Society of Civil Engineers, and a professional engineer. He received his bachelor's degree in France and a PhD in Canada. He has served as president of the International Society for Soil Mechanics and Geotechnical Engineering and as president of the American Society of Civil Engineers. Among his countless other awards, he's received the Ralph Peck Award from ASCE and the Jeff Meyerhoff Award from Canada. He has published extensively, including a book called Geotechnical Engineering. On a personal note, he enjoys tennis and plays jazz piano at the amateur level. Well, I'm sure he's being a little bit humble on that. So since we aren't fortunate enough to hear him tickle the ivories for us, we are very fortunate to hear his keynote address on erosion testing, simulations, and applications. So take it away. The floor is yours, Dr. Briaud.
Thank you very much, Jennifer. Let me share my screen. Let's see, share. And then right here, up. Let's see, I got to go full screen somewhere here. There we go. You see that? Can you confirm that you see the slide, Jennifer?
I see the slides. Yes, everything looks good.
Okay, very good. Thank you. Well, it's a pleasure to talk about erosion testing, simulation, and applications. I first want to recognize my two co-authors, who are two outstanding PhD students at Texas A&M University, Anna Shidlovskaya and Mostafa Bahmani. You will see their work as I proceed. So the presentation is divided into several points. The first part is on erosion testing. The second part is on numerical simulations. Then I'll talk about some applications and lead to conclusions. The first thing I want to do about erosion testing is talk to you a bit about the Texas A&M University Erosion Database. It's an international database of 1,256 erosion test results. You see the blue list here. Erosion functional apparent, jet erosion, hole erosion, slot erosion, 10 different types of tests that we organized. The data came from different countries, and the data is addressable. You can search this large spreadsheet. It has embedded erosion data and along with all the references. So you see here, I mean, you cannot see anything on that screen, but I just wanted to show you, this is one page of that. And here we have about 6 tests. So each line is a test, and there are 1,256 lines like this. On the left side, you have the record information. Then you have the erosion information. So for example, you might see here these plots. If you double click on those plots, they would come up and you would have the spreadsheet, embedded spreadsheet of the actual data. And then the pink part right here is the soil properties, anywhere from common soil properties to advanced shear strength and deformation type of properties. So using this database, we organize, and I'm going to talk a lot, refer a lot to this plot here of erosion rate on the vertical axis and velocity or shear stress on the horizontal axis. So because we had so many tests, we decided to plot all the tests for different soil categories. So here on the top left, you see high plasticity clay. As you can see, the scatter is significant. And then here is high plasticity silt. Here is silty sand. And in each case, we were showing the domain where these tests were falling. So again, If you're here, you have a high erodibility material because the erosion rate is high when the velocity is low. And here you have very erosion resistant material. The erosion rate is low, even though the velocity is quite high. So using all those test results, we were able to create this type of erosion category soil classification chart. Again, erosion rate on the vertical axis, velocity on the horizontal axis. And these are well-known acronyms, if you wish, classification for geotechnical engineers. GP would be poorly graded gravel, SM would be silty sand. Here is the high plasticity clay. And there's no doubt that as you go from the well-graded sand, this would be a clean sand, very erodible, as we know, and you go towards the high plasticity clays, then you have a much more erosion resistant material. Note that no soil essentially came into the low erodibility or category number 4, that most of the soil are in erosion categories 1, 2, and 3. This is the other plot that I will make use of, and that's critical velocity on the vertical axis versus the mean grain size on the horizontal axis, or D50. And as we know, for the coarse grain soil on the right-hand side of the plot, there's a strong relationship between the critical velocity and the size of the grains, but this relationship breaks down the minute we go into the fine sand, silts, and clays. And we've worked on trying to organize this scatter and find out what parameters impact the scatter on the left side of this plot. So having this 1,200 or so test results, we tried, and this was a fairly large NCHRP project, we tried different correlation equations. And we tried a lot of different correlation equation. And I circled here probably the best one that we ever found for the critical shear stress. But I'm here to tell you that regressions equations do not work. The scatter is just too large. It doesn't work. Please do not continue to work in that direction. It's a waste of time and a waste of our tax dollars. We've tried it. I've worked at it for 30 years and still unable to find a decent correlation. There's no doubt that, for example, the plasticity index has probably one of the strongest relationship to critical shear stress, but it's not sufficient. The reason is many different soil properties impact the critical shear stress and the critical velocity. And you can see that the best regression we had involved some 6 different soil properties. Again, it doesn't work. Don't worry about this. Let's work in other directions. All right. Second topic was the borehole erosion test. So there's been a lot of development in the laboratory over the last 30 years to develop erosion tests. The erosion function apparatus is one of them. We've developed over the last 6-7 years the borehole erosion test, and this is a test that geotechnical engineers do on a routine basis. We just don't measure the effect of erosion on the borehole. So the steps are: 1, you drill the hole; 2, you calibrate the caliper, the mechanical arm caliper; 2, and then you lower the caliper in the hole to get a 0 reading, an initial profile of the diameter profile of the borehole as you create it, usually 10 centimeter diameter. Then we run water, as we typically do when we drill by the wet rotary method. And then after about 10 minutes of circulating the water, we lower the calipers again in the hole, and we take the profile of diameter after the erosion test. So in essence, you see here, you have the rods, the water comes through the center of the rods, it turns around at the bottom of the hole, and it comes up, and in the process, it erodes the wall of the borehole. So if you look on the right-hand side, the solid line is the diameter of the hole before the test is conducted, and then the dotted line shows you the diameter after the 10 minutes of water flow. And the idea was that using the data, we could then obtain the erosion function, erosion rate versus velocity or shear stress better. And so that we could actually get this erosion function as a function of depth. What we have found is that this first arrow here to get the erosion profile works very well. The second arrow does not work. And I'm going to show you why. So we have equations and we can go all the way to shear stress on the borehole wall. I'm not going to go through all that stuff, but I wanted to show you, we in the process, we had to expand Moody chart to much more rougher interfaces on the wall. But in essence, this is what comes out of the borehole erosion test. And some of you on the geotech side are very familiar with the cone penetrometer test, which gives us a very helpful and useful profile of soil strength as a function of depth. The borehole erosion test is to erosion what the cone penetrometer test is to soil strength profiling. You can see on the left-hand side, we have radius versus depth. Went down about 3 meters, 10 feet. And this is the radius before in blue and the radius after the test in orange. We can then get the velocity, and of course the velocity is not constant through the hole because the diameter of the hole varies. We're able to calculate it, so we associate this velocity to these measurements. We then can get the erosion rate by getting the change in radius divided by the time of flow. And then we can get the shear stress through the use of Moody chart. And here's two sites. Here's a site where you can see that we have borehole diameter as a function of depth. And in this case, this is in feet actually. So we're going down to 14 feet, about 4 meters. And the first half of the borehole, the material is fairly erosion resistant. We have a weak layer right here in terms of erodibility, and then below that, an intermediate material in terms of erosion resistance. At the site on the right, we have a material that some layers that are very erosion prone towards the top with a resisting layer right here, and then below that, a fairly well erosion resistant layer. So profiling is quite useful. You've seen this tool, the erosion function apparatus. Brief summary: we take a steel tube. The steel tube is right here. This is the sampling tube that comes from the site. We put a piston at the bottom of the tube, and we push the soil out of the tube only as fast as it is eroded by the water that flows over it. So we calculate the shear stress at the interface between the water and the soil. And the piston movement is the erosion rate. And so from this, we can create a well-controlled and measured erosion function. So we had the tests from the site. This is a site in near Sacramento on the American River. Thank you to Todd Rivas and the Corps of Engineers. We work with them at those sites with the help of USGS and USDA, a big team. And we ran some borehole erosion tests at some of those sites. And then the Corps of Engineers sent us some samples that we tested in the EFA. And here is where, again, we're looking at erosion rate versus shear stress in this case. This is the EFA results. And this is the borehole erosion test results. And you see there is quite a bit of difference between the EFA and the borehole erosion test. And I don't have an answer for the different, I have a few ideas, but no, I cannot prove any of them. So I'll refrain from making any comments on this, just to tell you that be careful. The profiling when it comes to the BET works well, but the erosion function is quite different from the EFA erosion function. So you've seen the FA, and I want to show you now, and you've seen this movie. I'll start the movie just to show you here. So that, you know, we're pushing the sand out of the steel tube. The water is flowing this way, and you can see the erosion, dramatic erosion of that sand layer. We use that tool to test a number of things. We've been working quite a bit on erosion mitigation in the last couple of years. And here are some tests. Let me start this movie here. And here you're looking at riprap, simulated riprap. Of course, you know, we're looking at a tube that is only about 7.5 centimeters in diameter. And so you cannot put big riprap, but we put as big gravel particle as we could. So there is obviously a scaling issue. But what you saw in this movie is that we put the gravel / riprap right on top of fine sand. And in this case, you can see that the sand is being eroded through the riprap. On the right-hand side, we have riprap, and you can see the gray layer here. This is a geotextile filter that we put, and there's sand underneath it. And in this case, you don't see any erosion of the sand because it's kept in place by the filter between the riprap and the sand. So if I go to now to the, well, let me see. Yeah, right here. So again, I'm on erosion rate versus shear stress. And the green area is the sand by itself. The pink area is riprap on top of sand without filter. And then the purple area is the riprap with the geotextile filter. So only when we get to the filter, geotextile filter condition, do you take full advantage of the riprap. So filters are necessary when you put riprap. This is the best way to make the use of the riprap. And geotextile filters are the preferred solution. We did a survey on a project funded by TxDOT, and the solution, you can do granular filters, but the geotextile filters were favored in most cases. So that was for riprap. But we tested grass, and all this, by the way, is the work of Anna Shidlovskaya, Dr. Shidlovskaya, I should say now, because she's graduating. She tested the Bermuda grass, St. Augustine, zoysia, and bahia grass, different types of grass, to see, again, in the EFA. And I'm going to show you on the left-hand side, you're going to see Bermuda grass at 5.4 meters per second. So this is really going fast. And on the right-hand side, you're going to see zoysia grass at 3.8 meters per second. So on the left, it's going faster than on the right. And you will see that the zoysia grass is going to erode completely and be detached, where the Bermuda grass, here's the test, and here's the test. And you can see the Bermuda grass on the left-hand side is resisting very well. The zoysia grass is starting to lift off. And so, you know, there's always a question of how valid is a test at 75 millimeter scale. Of course, there are some issues, but if you want to do a levee overtopping up, and you see on the right-hand side now, the grass is completely gone. But the point is that the Bermuda grass turned out to be a 3-year-old grass. The zoysia grass was a 1-year-old grass. So the extent of the root system was not as large. And so different grass, different ages, different covers, there are many aspects of grass. Grass is a very natural product. And you can see here again, erosion rate versus velocity. And the pink area is no grass. The green area is when you have grass. And of course, different grass lead to scatter. But again, the point is that while the FA has limitations, testing the grass in the FA gives you a first indication of how the grass will be able to behave. you're talking about a test that's about $1,500 compared to a levee overtopping test full scale that's going to be in the $50,000 test. So there's a combination of those two things. So that was for grass. Looking at enzymes. Enzymes are very environmentally friendly cells that we actually have them in our liver. So they help us out. So, and this is a picture of a termite colony mound in Brazil. And the termites are actually using enzymes in their saliva to glue the particles together and build something that's quite strong. So we tested and no enzyme, the soil with no enzyme, again, erosion rate versus velocity or shear stress, no enzymes and enzymes. So the enzyme mixture, so when you mix enzyme with the soil, you can actually move the erosion resistance by about one category, which is quite helpful. However, it doesn't work on all soils. And the best, you have to have about 40% fine sand, 40% silt, and then about 15% or so clay particles. And the termites know that when the soil is right, the combination, so that they can actually build their structure. Lime is also another way to increase, we use lime extensively for pavements, for example, and we can use lime and mix it with soil to increase the erosion resistance. So you have here no lime in pink and lime in beige. Note that the lime can actually get you quite far in terms of erosion resistance, but again, it depends on the mixture, it depends on the soil type, it depends on the number of things, and these are the kinds of things that you can actually test at the with something like the EFA ahead of your of time, so that you don't go in the field and put make the wrong decision. All right, so all this was tests in the lab and in the field. We talked about the database, we talked about the borehole erosion test, we talked about the EFA and testing different soil admixtures and covers to be able to generate hopefully some environmentally friendly erosion resistant schemes. The second part of the lecture has to do with computational fluid dynamics merged with either mesh morphing or the discrete element method. The first part was the work of Dr. Shidlowska. This part is the work of Dr. Bamani. The way the CFD with mesh morphing technique works is you first have, you see the steps on the left-hand side here. You have the CFD equations to obtain the hydraulic shear stress at the interface of this mesh here. Then you use that shear stress and the erosion function to find the corresponding erosion rate. You then use the erosion rate over the time step to compute the erosion displacement. And number 4, you adjust the mesh shape to conform to the new erosion, the new eroded configuration. And then you repeat 1 through 4 as you step into time. So you're looking, the nice picture here in the center, you're looking, the 2 white rectangles going down are the rods in the BET. And the water is coming down in the red inside the rods, and it's turning the corner and going up in the blue on the outside, because the velocity is not as high in the annulus in this case. And then the white on the outside is the soil. So let's see what it does. So here is what happens during that test with the CFD mesh morphing technique. And you can see, I'll play it again, whoops. Well, maybe we'll do it in there. So this is the same animation, but now I'm showing you the shear stress on the vertical wall here, on that wall, the shear stress distribution. And you can see that towards the bottom of when the water turns the corner, the shear stress is quite high and quite erratic. But as soon as you get back, and the impact is, what would you say, about 1 diameter or so of the borehole. Once you're up more than 1 diameter, then the shear stress is quite constant, and you can make use of that, of those readings. So you have to ignore. Actually, what happens at the bottom is a jet test, and you can see the shear stress here versus distance, radial distance. And what happens is the shear stress is at the very beginning, before you start digging the hole at the bottom of the borehole erosion test, the shear stress is quite low in the center and quite high away from the center of the radius. But as the test proceeds, then the shear stress is equalizing as the borehole, so the BET, if you wish, you can actually use, I don't do it particularly, but you could actually use the bottom readings as a jet test. Mesh morphing, here is on the top right, erosion rate versus shear stress. This is an erosion function measured in EFA for that particular soil. And then this is the mesh morphing simulation. You see the green line here, it's a small green line, and then the blue line, which is predicted by this technique after a certain amount of time. The problem is in the mesh morphing, when we do these simulations, we assume a uniform soil. And obviously that defeats the purpose of the BET. So yeah, we did it, but the idea of using this technique for simulating BET is not a good one. But it does help in this particular case. So again, this is CFD mesh morphing, and we're simulating a water jet. So you can see the water. So this is a jet test. The water jet is coming here, and it's coming into a body of water as the classical test, and the white on the bottom is the soil. So I'll play the animation, and here is what the simulation is telling us is happening. And you can see that as can be predicted, the hole is deeper, right in line with the jet, and is less on the sides. And again, that's what's happening at the bottom of the borehole erosion test. Note again that as we saw in the bottom of the borehole erosion test, shear stress versus distance, at the beginning of the test, the shear stress is quite high. It is low in the center, but quite high right next to the center of the test, and then it decreases on the side. And as the borehole, as the hole is being dug by the jet, the shear stress decreases from this value to something that's more distributed after a certain amount of time. And that's one reason I'm not a big fan of the jet test, is because the shear stress varies quite a bit, and so it's difficult to create an erosion function when the shear stress is varying as the depth of the hole is created. So then we obtain the erosion function from the EFA test, and we use that erosion function together with the CFD mesh morphing technique to predict the scour depth as a function of time. So this is the scour depth that you saw in the movie here. So we're predicting that depth as a function of time. This is what you see on this side. And the black dots are the test itself. So we run jet tests in our lab, and we recorded those black dots. And these are 4 predictions using the CFD mesh morphing. And you see the one that fits the data best is the one where we assume the smooth interface between the water and the soil. Last mesh morphing, so here's a hole erosion test. So the soil sample is top and bottom here, and there's a hole in the center, and the water is flowing from left to right. You can see the shear stress distribution as a function of distance. So in the center of the hole, the shear stress is well behaved. And again, we played the same game. We got an erosion function from the EFA test, and we used that in the CFD mesh morphing technique to predict the hole diameter as a function of time. The dotted black dots are the tests, and the green prediction is when we assume a smooth interface between the soil and the water. All right, so that was CFD mesh morphing. The second technique I wanted to discuss, and I'm really excited about this one. I mean, it's called the discrete element method, and many of you have seen it, used it, but there's so much potential with that method. It's remarkable. It's kind of a revolution in geotechnical engineering. So the method, it works this way. You actually model the particles instead of a continuum. The particles are, you set the number of particles to start with, and step one here, you have the state of particles known at time zero. So you have the location, contact forces, displacement, velocity, acceleration, you're ready to go. And then you start and you move into time delta t. The problem is that delta t is inversely proportional to the particle stiffness. And particle stiffness is, crystal, like a quartz grain, is very stiff. And so because it's very stiff, delta t has to be extremely small. If delta t is not small enough, when you step into time, the particles move so much that you might find one particle in Japan, one in Russia, one in Argentina, and then the thing blows up. So you have to have very small time steps. And then three, you update the forces after the time increment, including the drag force from the fluid, and you use the CFD to give you those forces. And then you have particles, equation of motion, constitutive models, contact force model, to obtain the new set of particles, location, contact forces, displacement, velocity, acceleration. And then you repeat step 1 through 3 as you step forward into delta t. And so when I first looked at this, with the finite, we use the finite element method extensively. One of the big problems with the FEM is that you have to invert a huge matrix, and that's what takes a huge amount of time, computer time. And then I saw this technique and I said, my goodness, all we're doing is stepping into time and updating forces and displacements. And so that should go a lot faster. We can be more. Problem, and I was disappointing, I guess, when I saw that. The challenge is that, as I said, the particles are very stiff. So delta t has to be very small. And so that limits the computation efficiency in the process. And so we've tweaked, and everything I'm going to show you after this, we've minimized the computer time by using softer particles. So the grain, the particles themselves, we've made them not out of marshmallow, but certainly not quartz. Also, the number of particles is a limitation. If I asked you how many particles fit into 1 foot cube, 0.3 meter by 0.3 meter by 0.3 meter. So you have this big cube, and you're going to put clay particles in it. Well, the number is 27 trillion particles, equal to our country's debt in dollars. 27 trillion particles in 1 foot cube. So the number of particles is astronomical. And so that's what limits the calculation. And so in everything I'm going to show you, you'll see that we have bigger particles because of the limitation. The flow is not through the voids. We don't actually follow the actual voids and let the flow go through the voids. That would be extremely time-consuming and computational intensive. But we do an equivalent, a bit like we do when we do seepage calculations. an equivalent flow through a similar porosity material. All right, so you have equations, 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 equations. You get it. But a lot of mathematics behind it, but that's not particularly fun. So let's see the results of this thing. So the first thing you do is you say, well, I would like to be able to calibrate and demonstrate that the CFD-DEM approach works. So we use some test results, experimental results from Van Buchtenen et al. And well, let me play the movie, the animation. You're going to see what they did. So this is CFD-DEM on the right-hand side here. And so what they did is prepare a container. They had a jet at the bottom, and they jetted. They had sand, and you see their equipment here, a camera, so that they could follow the particle movement through particle image velocimetry and positron emission particle tracking. And you can see here on the bottom right the predictions of CFD-DEM, the blue line, and the measurements in green and orange. So we felt that the predictions were reasonably close, and that gave us some confidence in what we could do. So then we did things like this, where we modeled some Teflon balls, comparison. I'm going to move to some of the more interesting stuff. We used a camera on the EFA, and we ran some tests here with different materials. On the left, you have a rounded gravel. On the center, you have a angular gravel, and on the right-hand side, you have some Teflon balls. And it's actually a really nice technique called image analysis with Tracker. Tracker is a software that's pretty inexpensive. And what you do is you track the particles. So this particle right here in the next frame is moving over there. In the next frame, it's actually detached and it's gone. And so you do this analysis with Tracker, and that software allows you to get the displacement as a function of time. So here is the horizontal displacement. So you're looking at 1 centimeter here. So the displacement, the particle shakes to start with before it's eroded. And you see the displacement as a function of time over 2.4 seconds, and then it's detached and it moves significantly at about 2.5 seconds. This is the vertical displacement versus time. And then once you have the displacement, you can get velocity. Take the first derivative, that gives you velocity. So you have horizontal velocity versus time on the left, vertical velocity versus time on the right. One more derivation and you get the acceleration. You get acceleration versus time in the horizontal and vertical direction. You multiply by the mass of the particle and you get the drag force in the horizontal direction, and you get the normal force in the vertical direction. And the red line here is the weight of the particle. And you can see now the hydrodynamic forces that are exerted on that particle in the horizontal direction, drag force, and in the vertical direction. Note that the magnitude, which in this case is about 20 millinewton, is about the same in the horizontal direction as it is in the vertical direction. And the weight of the particle, as I said, this is 20 millinewton. And here, the lift force becomes large enough that it's actually detaching the particle. So I think this image analysis is really a nice potential. You know, for a long time, I've tried to think of how to measure shear stress. And then, of course, if you divide by the area of the particle, in this case, you know, we should really divide by the area of contact with particle, but that's something we don't know well. So we divide by the entire cross-section area of the particle, and then you get shear stress here, shear stress, and then normal stress on the right-hand side. And I do think that the normal stress plays an important role, but yet all our models are based on shear stress mainly. So what we did next was to use the CFD-DEM and try to model the results of the video analysis. And you can see here on the left side, you have, again, we're back to erosion rate versus velocity. And this is the red is the CFD-DEM results for the Teflon balls, and the blue is the experimental results for the Teflon balls. This is in terms of shear stress on the right-hand side. So that worked pretty well. Then we did that, we repeated for the gravel. CFD-DEM is here in the red, and the blue is the gravel. Again, we felt really good about the comparison. And then once we had this degree of confidence, we said, all right, well, let's try to study different parameters that could impact the erosion process. And the first one is that we tried was suspended particles in the flow, with the idea that if you have sand in the flow, you know, the clear water scour sort of thing has no sand in the water. But if you have sand in the flow, maybe you'd have an abrasion effect, and that would make a difference in the erosion rate. And the CFD-DEM tells us, yes, it does, but it's not dramatic. You can see here no concentration in blue, and then a 5 gram per liter, 5 millimeter particles in red. So impact. But the main thing to me that's really a nice discovery is the effect of cohesion between particles. And I'm going to explain what I mean by cohesion. But you can see here we have 3 millimeter particles, and here is no cohesion on the left. So you have a sand, a little bit of cohesion, and then all the way to, it's not that much cohesion. This is 3,000 Pascal, but that's 3 kilopascal. And 3 kilopascal as a cohesion intercept for a soil is quite small. Yet this amount of small cohesion makes a huge difference in terms of erosion resistance. And so here's the, for the geotechnical engineers in the group here. So you know this is shear strength versus effective stress. And this is the Coulomb's equation. We have at 0 normal stress, the cohesion intercept C prime. And so for any shear strength, we have a component that's friction and a component that's cohesion. And if you're in surface erosion, the friction depends on the normal stress. There is very little normal stress effect between particles when you're at very shallow depth. When you're at 0.001 millimeters, the normal stress is very small. And so the erosion process is controlled by C prime. That's a good way to explain the process and really understand. The problem is, as geotechnical engineer, C prime is one of the most difficult parameters to obtain with reasonable precision. And so I think we need to really pay attention to C prime for surface erosion. Now, if you go to internal erosion and the depth of an earth dam, now you have a lot of friction between the particles. And C prime is only a small component of the resistance to the erosion process. We went to look at this bottom left here. That's the critical shear stress as a function of cohesion. It's just beautiful correlation. The cohesion intercept explains the critical shear stress when it comes to surface erosion. And so going back to this, what I showed you earlier, critical shear stress versus mean grain size, if you can start making sense of this big scatter on the left side for the fine grained soils by putting lines of cohesion, and we're starting to collect data in that direction. All right, let's move on to other applications of CFD-DEM. Infilling. Infilling is an issue in bridge scour, and it's actually frustrating because it takes place from time to time. We don't have a good way to measure it. Yet we make a decision typically on the depth of infill holes, not on the depth of the hole at the time of the big event. So we simulated that process with the flow velocity is decreasing because the infilling takes place, the deepening of the hole takes place during the storm, and the infilling takes place as the water slows down. So we're going to simulate the water slowing down and see how much. So here's two animation of the CFD DEM. On the right-hand side, you have small particles at the bottom of the river, and they fall in the hole. There's quite a bit of it. And here's some larger particles, so you don't have that many that fall in the scour hole. And so the percent infilling of the scour hole is inversely proportional to the diameter of particles on the floor of the on the bottom of the river. Because most of infilling comes from live bed scour. The suspended solids that fall in the hole accounts only for a very small fraction of the scour infilling. All right, next. Influence of the scour hole depth and the slope of the scour hole on the amount of infilling. If you have a scour hole here, whoops, that is fairly shallow and the slopes are shallow, then there won't be much infilling because the water, the particles have enough momentum to be able to go down the hole and up the hole. But if the hole is deep and the slopes are steep, then you're going to have a fair amount of infilling, and here are some results from this. All right, one more topic: riprap on abutment slopes. You can see a problem here. We're starting to lose the riprap, and these are not animation, but the issue is that the critical velocity of riprap depends on the angle of the slope, and we were able to show this through the CFD DEM. Here is a flat condition. The riprap is on the flat ground. There is a 6-to-1 slope, a 3-to-1 slope, and a 1.5-to-1 slope. You can see that a 1.5-to-1 slope, with the water was flowing this way, you have a lot of riprap movement. So the critical, and we're working on this as we speak, the critical velocity of riprap depends on the slope of the abutment. Actually, my colleague, B. Hunt, asked me that question about 15 years ago. So it took me a while to answer that question, but some of it is here. And so here is critical velocity, few results, not much data yet, but we're working. Critical velocity on the vertical axis versus slope angle of the abutment slope. Terzaghi filter. Jennifer, how much time do I have?
We're good to go for another 10 minutes or so.
10 minutes, okay, good. Let's look now at filtration in dams. So again, because we're inside a dam, we're gonna have to set a pressure pretty high to represent the true condition between the particles. And we're going to simulate, we simplified the problem significantly. We're going to simulate a downward flow with smaller particles on top of bigger particles to see if the smaller particles will actually travel through the larger particle as a function of time. And you know, the Terzaghi filter criterion is well known in seepage analysis for dams, and it basically says that when you have a contact problem, you have to be sure that you don't have too much of a gap in sizes between the native material and the filter or the riprap. You know, we heard about the filters before. And Terzaghi said 4 as a ratio between the two particles. So we started with uniform particles here with a ratio of 4. The ones at the top are 5 millimeters. The one at the bottom are 20 millimeters. So here's what happens. You can see that there's not too much, some of the particles go through the big ones on the way down as the flow comes down this way. but not that much. Now let's look at 5 and 25. So it's pretty close. We have here a 5-to-1 ratio. Here we had 4-to-1 ratio. Here is what happens. In this case, a lot more of the blue particles actually penetrate through the red particles. So Terzaghi really had it right. You can see here normalized mass loss as a function of the gap ratio. 4 dense, 4 loose, and then 5, and boom, you have a lot of migration through these two cases. This was for uniform material. The problem of suffusion has to do with gap-graded material. And I'm going to show you 2 animations. One for the case of a uniform, a well-graded material, the gray line here, where you don't have a gap. And then I'm going to show you the brown one, where you have a significant gap between about 30 millimeters here and about, 6 millimeters, so 6 to 30. All right, let's look at this. This is a well-graded case. So we have small particles that are 2 to 6. The big ones are graduated from 6 to 30. And here is the simulation of the suffusion process. You don't see much migration in this case. If you have a gap-graded material, here's what happens. So if you have, the CFD-DM allows you, if you have a dam and you have a certain material on one side and another material on the other side, you can do these sorts of simulation and see if you're really going to run into a suffusion problem or not. Talking about dams, this is totally at the other end of the spectrum, because this is a very simplified way of evaluating dams and levees from the erosion point of view. The idea is 4 steps. So these are applications, part of applications. You have the erosion categories. This is a cross section of a dam, and you have a layer that's covering the dam, so a pretty large material. And then you have the core here. The erosion category for the core is 3. The erosion categories for the covers are 4 on either side. And the idea is that you take a cross section and you have a distance of 17 meters of erosion category 4, a distance of 100 meters of erosion category 3, and then a distance of 15 meters of erosion category 4. And you simply do a dam erosion category as the weighted average of these erosion categories. In this case, we got 3.2. So when you plot it on this curve, again, erosion rate versus shear stress, and so this is erosion category 1, this is erosion category 2, so the line is 1.5, this is 2.5, and then we say that our dam was at 3.2, so it's that thick blue line here. We did that for the Teton Dam. Went there, did some testing, and the Teton Dam failed by internal erosion, and we got 2.6 through this technique. So there must be an erosion failure boundary for dams somewhere in here, and we're working on that. Another simple spreadsheet for TEMU-PM, prediction of erosion movement. And you use the erosion function, the velocity hydrograph for the case, and you predict the erosion movements. It's a very simple spreadsheet. You see the erosion function here, the velocity hydrograph, and then the erosion movement over here. So we're back to the American River, courtesy of Todd Rivas and his team at the Corps of Engineers. And we're looking at a site on the American River right here on the left-hand side. And there is a gauge at that site. So we were able to get the actual hydrograph. And there is a lateral migration of about 6 meters between 2007 and 2017, 10 years. We knew it was 6 meters, so we used PEM, and by trial and error, defined the erosion function that was necessary to match the observation. And here's what we found. The generated curve, by matching the observations is somewhere between the pure soil, which we tested in the FA, and the grass test that we ran later on. So it seems to make sense in that case. And that gives a sense of the power of observation methods. And here's another case where observation methods can really be helpful. On the left-hand side, you have the current practice. You're looking at predicted scour depth versus measured scour depth. And these are 10 bridges that we tested over a period of time. You see the R-square is at 0.3. We've developed this observation method, and the scatter becomes dramatically less. We're 7% on the safe side. The R-square has jumped to 0.86. So I really feel that there is tremendous value on observation methods. And in the case of the scour depth that I just showed you, the current practice is based on flume test. That means we have a scaling problem. It's based on the wrong worst soil because it's fine sand. And that's the easiest thing that we can use in our flume test. It's a simplified geometry, simplified single velocity, whereas the observation method is at full scale. You use past history observed at the bridge to predict what's going to happen to the bridge if it sees a big flood. So it's at full scale. It uses the right soil. It has the exact geometry because it's the bridge itself and the exact velocity hydrograph. So this is my last slide. I've shown you some advances in soil erosion testing. The BET is very valuable field test for erosion profiling. Riprap needs filter. Geotechnical is best. Grass, enzymes, lime decrease erosion potential when used in the right conditions. Doesn't always work. TAMU erosion database is valuable, but shows that correlations are hopeless. Well, I'm a little bit tough. Yeah. Measuring is best. Erosion classifications help at the preliminary level. In terms of numerical simulations, I showed you some computational fluid dynamics mesh morphing technique that shows that the FA erosion function can predict the results of the jet test, the whole erosion test, and to some extent the whole erosion test. The computational fluid dynamic discrete element method is extremely valuable, and I think it's really future direction. We'll make great strides if we continue to work in that direction. Understanding the erosion process, including infilling, filter criteria, critical soil properties, and more. Some applications, I showed you the prediction of erosion movement spreadsheet, observation methods, dam erosion classification. And when it comes to a look at the future, I think the role of C prime, I'm really excited about this. The role of C prime to me is the key to erosion resistance of fine grained soil. It opens the door of explaining the process of erosion, at least for surface erosion. And then my last comment is about field observations. Field observations are a critical component for rapid progress. I showed you some of the observation method for scour, and honestly, I feel that it's really important. We've worked on the modeling methods for a long time, 40 years, and we have made slight progress. Observation methods are low-hanging fruit, and it's time for some of us, all of us, including FHWA, to start working on observation method. There's so much value. And as I said, it's a low-hanging fruit. I think that, so it's a challenge, I guess, to you, Jennifer, and Silas, and all the good people at the FHWA. Observation methods are key to making rapid progress, decreasing scatter. We need to work in that direction. Thank you for your attention.
Great, thank you so much, Dr. Briaud. That was an excellent presentation. And speaking from FHWA, I can't comment specifically on your observation method for scour, so we'll leave it at that for now, but definitely your work has informed, what we do and continue to do in our research. So with that, we did get some questions that came in during your keynote address. And if anybody has questions in the meantime, while we're going through that, just please put them in the chat pod. So we'll go ahead and kick off some of the questions. And this one comes from Peter Toe. And it's really a clarification on how you measure the hydraulic head in your erosion test apparatus. You know, they tried to do the same thing, followed your paper, but the number was crazy and they saw very high fluctuations, especially sometimes the hydraulic head at the downstream is larger than the hydraulic head at the upstream. So can you comment on that?
Yeah. We measure the velocity through a flow meter, and so we essentially get flow as a function of time, and there is some fluctuation, and we take the average flow value. There's a lot of progress that needs to be made in all those tests and techniques. I can tell you what we do, but I'm sure there is room for improvement in all of this. We just measure it through a flow meter.
Okay, great. And a similar type of question when you mentioned velocity in your paper, and you talk about the average velocity, but the actual velocity actually changes with depth. And so when they use the rectangular cross-sectional area, how do they calculate the shear stress from velocity, especially given that the Moody formula is good for circular cross-section, whereas the EFA has that rectangular cross-section? Can you comment on that in terms of the velocity?
Yeah, sure. So, there's no doubt, there's this dilemma when you prepare a presentation. Do I show velocity? Do I show shear stress? Do I show both graphs every time? And the graphs are not as big on the PowerPoint. The velocity, you're right, varies through the profile. So we use mean velocity. The advantage of velocity is that people get a good sense of what it is. If I say 10 meters per second, people say, whoa, this is a big one. If I say 10 pascals in terms of shear stress, people have no clue how big or how small the shear stress is. So that's the advantage of velocity. From the purist point of view and the scientific point of view, it's much better to use the shear stress because the shear stress at the interface is well defined. And the way we get the shear stress the way we measure the shear stress is by calculating it from the mean velocity and using Moody chart. And Moody chart is for circular pipes, and we use the hydraulic radius of the rectangular cross section to be able to get back on our feet and use the Moody chart. I'm really hopeful that with this camera technique, the video analysis technique, we can actually get some better inferences. And you saw how much it fluctuated with those particles. When you get all the way down to the shear stress, it's not a constant shear stress. So again, by doing what we do today, we're doing average values, and there's a certain level of uncertainty because, or at least there's a distribution with a mean and a standard deviation in the values of these shear stresses. But hopefully with the video and image analysis, we can get closer to, and not without spending too much more money.
Right. Sounds good. So another question we received from the YouTube live stream from Ignacio from Panama. Do you think that Terzagh's concern due to Scour has been resolved or has been solved?
I didn't catch that. The Terzaghi?
Do you think that Terzagh's concern due to Scour has been solved?
Wow. Well, I'm not sure. I didn't even know. I knew Peck had worked on Scour because actually his father, Peck's father was a railroad engineer that worked on a bridge in Colorado, and that's how Peck first got connected with Scour. But I didn't know Terzaghi is Scour. So please send me that information so I can dig into it. It'd be an interesting part of history. Now, Scour, we solved the problem. We're progressing. We're human beings, and we're concentrating on safety of the public. but at the same time, we have to accept that we're not perfect, we don't know everything, that we don't cover all the bases, and that unfortunately, failures do occur. So I would say no, we haven't solved the problem. Will we ever solve the problem? Not 100%, because you can never assure that the probability of failure of a bridge is 0 for the reasons that I've mentioned. But we certainly need to continue to work in the direction of minimizing that. And that's why working in reliability and risk-based design is critically important and will be the next wave of code development. You know, we worked on working stress design, then we graduated to load and resistance factor design by basing our decision on the probability of failure. And the next wave of design will be risk-based design, where we include the value of the consequence together with the probability of failure so that we can make risk-informed decisions.
Right, that sounds good. And we have time for maybe 1 or 2 more questions. So we have another one from York Rokama. He said, very interesting presentation regarding increasing the erosion resistance. You showed different methods that you can move the materials from a low erodibility to a higher erodibility. But can you move the opposite direction from poor to very poor erodibility, or is that only limited from class 2 to 3?
Well, now that's an interesting question. You know, I've never thought in that direction, but I suspect that on some jobs that could be important to make sure the material is moved by water. You know, when we do hydrometer analysis, for example, we use dispersing agents, and I suspect that that could be one such use. If we want to move particles more easily and make sure they're detached, and anything that will decrease this cohesion that I'm talking about probably will accomplish some of what you're talking about. But you know, this cohesion, I keep going back to this. It's so critically important, and yet it's one of the least well-known parameters in geotechnical engineering. It has a huge impact on slope stability, for example. And yet, when we do traxel tests, you know, we put the best fit line between our Mohr circles, and C prime can vary quite a bit. And yet, in this case, it turns out to be so important.
Seems like it. And then, yeah, one final question. This comes from me. You know, what are the biggest limitations in applying results of erosion testing to scour analysis and design? You know, especially when you see those differences depending on how you measure erosion. You showed the difference between EFA and BET results. So what are your comments on that?
Yeah, that's a critically important issue. You know, we have 40 years ago, we didn't have any soil property in the scour equations. We've come a long way thanks to your help, Jennifer, and all the people at FHWA and others across the world in universities. But so we've progressed first in the lab, and now we're starting to see developments in situ. And we're starting to see some differences. And we're scratching our heads, why do we not find the same in the lab and in the field? So the best way I can answer this question is to say observation, observation, observation. You know, the thing about, what is it, when you're in the building business, location, location, location. Well, in my mind, the future 20 years is observation, observation, observation. We really have not taken advantage. Look at USGS. USGS, Steve Benedict did one single effort of measuring scour depth at bridges. Everybody, since he did that, is using his database to calibrate, to understand. So extreme value in observation and making observation from the past to predict the future. That makes so much sense. And we have not worked on this very much. We've worked in modeling, like you point out in your question, the lab test. You know, we've developed a lot of stuff in the lab test, but we test 10 to the minus 6, 1 over 1 million volume of soil. So we have a volume of soil that's 100 meters by 100 meters by 100 meters. We test a few samples. And on that basis, we got to make the best prediction within plus or minus 20%. It's very, very difficult. People tell me this is not rocket science. I say, no, it's not geotechnical engineering. Maybe I should say it's not scour engineering. So I think observation is the way to the future.
Well, great. Very interesting talk, very interesting insights that you've provided us. Thank you, Dr. Briaud, again, for your great presentation. That concludes this session, but I am going to turn it over to Ming for some final comments before we close out.
Thank you, Jennifer. We thank Mr. Kalla and Dr. Briaud for very insightful and informative talks. Just a quick announcement. When you can see the shared screen in a moment. There is the ISS MGE TC213 Committee on Scour and Erosion, and the meeting is tomorrow, Tuesday, at 5 p.m. Eastern Time, the US Eastern Time, and it's open to all participants. If you're interested in attending, and please email Kathy, and the email address is showing here, and so that she can send you the Zoom link. And this information is also on the conference website or the conference platform. And if you encounter technical difficulties of using the conference platform, please let Aaron at ASCE or me know, and we'll address them ASAP. And for session chairs, and please task to join the session, and you will moderate in advance. And if you cannot join, and please also let us know so we can resolve them. Great, that concludes our morning session, and thank you all, and look forward to see you all in the afternoon in the technical sessions. Bye-bye.